Hello everyone. Could one of you please check if video and sound quality are fine? I will be starting very soon. Hello. Furkan, maybe you comment about that. Yes, thanks a lot, Furkan. So today I will be talking about, this is actually the fifth of our FPGA from zero to hero lectures. So we will be talking about linting rules for FPGA design and verification. So let's continue with the agenda. Yes, here it is. Just let me rescale the presentation. Yes. Okay, so we will be talking on the HDL hardware description language, linting rules. So those when we say HDL, we like mention the VHDL, very high speed integrated, integrated circuit hardware description language. So it's the VHDL, Verilog, and SystemVerilog. So here when we say HDL, like 99% of the time we are mentioning these three. So some of the linting rules that I collected, I wrote down in the past, so we will be discussing about them very soon. Then there will be wrap up and Q&A. So for today, actually, since I won't be able to have a class this Sunday, as you know, normally we are having Q&A session, Q&A class on Sundays around 10 a.m. normally, but this evening we will be combining those two. So first I will finish the slides that I have prepared, and then we will have a 10-minute break, and the other stream I will starting that one. So the sixth lecture of those 30, we will be having the Q&A session. So through the slides you may ask any question using the chat. So during the Q&A session later today, I will be reading and answering them. So yes, this is the plan for today. So let's continue the linting rules that I have prepared. Of course, there are many linting rules, by the way. There are really nice open source, so free of charge, and paid linting tools, and they have really nice different rule sets. Some companies customizing those rule sets, or they are writing their own rule sets from scratch. Different combinations are possible, hybrid solutions are possible. But here from hardware description language perspective, I majorly for VHDL, but these also not all of them, but majority also applies to Verilog and SystemVerilog. So these linting rules, like I think 10 or 12, I don't remember the exact number, but I tried to, I will tell you the most fundamental ones according to my perspective, of course. So first one, very important. This is an old rule, actually, like Xilinx, Altera, you know, the two most preferred FPGA vendors. They are mentioning this linting rule for many years, actually more than 12, 20 years. So, but it is unfortunately not used by some of those VHDL based design or verification engineers. So the standard library usage, actually, if you are not doing any arithmetic operations, this library IEEE and use IEEE.std_logic_1164.all, these two lines are enough. But if you would like to do some arithmetic operations, which include sometimes unsigned, sometimes signed vector operations, then you shall also add this use IEEE.numeric_std.all. Yeah, many VHDL gurus, they by the way spell it like numeric stat, not std. Yeah, I hear from many 20-year, 30-year experienced great VHDL engineers. They call it numeric stat. So std, it's this standard open form of that stds, but they stats, so they prefer it. So just to mention you, if you hear something like that for the first time, they pronounce it like that. So these, for the VHDL libraries, standardized ones from IEEE, these three lines is enough. You see that first you are saying you will be using IEEE Institute of Electrical and Electronics Engineering, and then you are mentioning to use their actually sub-libraries, kind of packages, IEEE dots, std logic 1164.all and numeric stat.all. So that shall be enough for everything. Of course, sometimes you have some custom packages in your company, in your team, in your project. Of course, if you are using some functions, some procedures, some constants from those custom packages, of course you are adding them. Or if you are trying to simulate a specific intellectual property, you shall add their related libraries. But for in general, for writing VHDL code, either simulation codes or design codes, these three lines shall be enough. So this is the standard logic 1164 and numeric stat. They are supported very well by IEEE. Also some deprecated libraries like ARIT, for instance, one of old Synopsys library, also using directly either signed or unsigned libraries. They shall not be there. They are not recommended by any any uh, any of those vendors like Xilinx, Microchip, or Altera, but also good, very good, very well-known training companies. They shall not, they are not recommended. Okay, this is the first one. As I mentioned, for VHDL, only 3 lines below shall be used 99% of the time. That 1% is depending, yeah, if you are, of course, if you have some custom libraries, as I mentioned that, or if you are trying to simulate a specific intellectual property IP or VIP, verification IP, then you shall add related libraries. So this is for VHDL standard library usage. Yes, this indentation, the second one, that check indentation rules inside the code to improve design readability and warn the user if any line of code exceeds the defined character limit. Yeah, we, for instance, during the previous class, previous Q&A session, question answer session, last Sunday we reviewed one of our friends' code, and I mentioned there some of the lines he was exceeding those viewable, easily observable line of code limit. So yeah, it is good if, for instance, if you are using a 28-inch monitor, let's say, it shall not exceed half of it or 70% of it. So of course it depends on resolution as well, but this is a team decision. So it shall not, you shall not scroll your code horizontally. You are anyway doing, because yeah, it's usually it is more than like 300 400 lines of code. If it is a moderate one or more complicated one, so you are anyway doing some scroll vertically, but you shall not do horizontal scrolling as well. So then it will be, as a general rule, it will be more readable. So it is not, of course, HDL, hardware description language specific stuff, but more in general coding coding rule or good coding practice, let me say. So yes, indentation rules are really important as you add some if statements, case statements, and of course they have some hierarchy. For instance, you write a case statement. In one of those cases, for instance, you are checking for a special value of a 1-bit STD logic, let's say. Then you need to add some indentation before starting the case statement. Then inside the related state of that finite state machine, then you if you are doing another if statement, then you shall add some indentation. Also, you know, sometimes you use some select statements or if statements, and then you have another level of hierarchy to check another value after that if or else statement. So yeah, by the way, in general, it is not preferred to have more than 3-4 level of hierarchy after the rising edge clock statement, because as you add more conditional dependencies, that combinatorial path lookup table logic, it becomes longer and longer. So depending on your coding style, depending on your FPGA speed grade, FPGA family, so you may not end up with good clock speeds. So for instance, if you add like 10 hierarchical if statements, then you may end up with 20 megahertz or 30 megahertz, depending on your, of course, the resources, the family, speed grade, etc. So yeah, 3-4 level is usually good, as long as you are trying to reach, you are trying to implement a fast clock algorithm. Like if your core clock is 500 megahertz, 1 gigahertz, it is possible with those Stratix 10, Ultrascape Plus, and Versal families, the latest Xilinx and Altera FPGAs. So you shall not add too much conditional if statements or case statements or whatever you try. So yeah, this is also a good coding practice, good design practice in terms of not only readability but also performance parameters. Okay. One question from Furkan is asking if there are any problem about using Unisim and Unimacro libraries. Of course, it is there is no problem with that, because those are built-in Xilinx libraries, so simulation libraries and macro libraries. So when they need it, they shall add. You shall try to add them. These 3 lines of library statements you are seeing, these are for the general purpose libraries. That Unisim, Unimacro, those are going to, those are in the you are using them for simulation, or for using instantiating some vendor specific IPs, intellectual properties. So they are in that side. Of course, as I mentioned, it is fine to use them. These are like the ones you mentioned, libraries specific to vendors, like Xilinx, like Altera, like Microchip, or the others. So of course, also some custom team specific libraries, custom specific packages, they shall be added as well and reused. These are quite beneficial and helpful, because otherwise you need to write those custom packages, or maybe you need to copy paste some other vendor specific libraries from elsewhere. Yeah, that library usage is helpful as long as you are using required ones. So for instance, when you need Unisim for some simulation, there are also some other simulation specific libraries of Xilinx. You are not adding them, you are adding only the one you need, and 99% of the time those examples, templates of Vivado, Libero, and Quartus, they are providing you those libraries you mentioned, that kind of libraries. So yeah, it is they have to, you shall use them, otherwise you will be getting some errors. By the way, if you are confused about some legacy code, some old designs you have, and if you think that you don't need those additional libraries, you may, for instance, for synthesis, you may remove some of them and check if someone added some unnecessary libraries without their even if there is no dependency related to them. So if you think they added unnecessary ones, just do some simple elaboration or synthesis to check them if they are really necessary or not. In case they are unnecessary, it is good coding practice to remove those unrelated libraries from your code. Okay, we had the first two. We will continue with the third one. The third one is also nice because unless you do that, yeah, let me read first. Detect the signals which do not have any relation but are used in the same process, and then use them in separate processes. Yes, sometimes this is also a frequently done mistake. Yep. Designers are eager to do everything in one or two processes, so they just add all the signals that are, even if they are related or unrelated, they put it in the same process. So then actually you are somehow limiting the optimization power of your EDA tools algorithm. And sometimes unexpectedly you are creating some dependency between those signals, even if they are actually unrelated. So as soon as it is possible, don't add unrelated signals. Don't read them or write them in the same process. So try to like divide and conquer. Of course, if there are some, if you need to read some signals in different process, reading is possible, but writing to the same signal in different processes, it is not possible. It will be a compilation error. Actually, it's a syntax error. It is detected by EDA tools fast. Of course, you can read signals in different processes, but as long as they are unrelated, so try to write precise, short, different processes, as long as I mentioned, their purpose are different. Otherwise, by the way, the length of the process increases. It becomes harder to read by your colleagues. So reusability is damaged, readability is damaged. So yeah, it is from my perspective, after 15 years of experience on FPGA design, for me it is really ugly to have long processes. So it is like 1-2 processes, and each are like maybe 1,000 or more lines. So it is not acceptable. So it shall be, you need to divide those specific tasks of the processes and do more readable, more reusable stuff. So it is achievable, of course, as long as you know the design requirements, you know how to implement it. It depends also on the preliminary work you have done regarding that design. If you didn't do any planning, if you don't know requirements, if you didn't have any brainstorming with your colleagues, if you haven't done any literature review about that algorithm, then of course you start to like a bin, like a let me say trash. You are adding everything to one process or two processes. Then it becomes really ugly. It becomes it becomes nearly impossible to reuse, and then that becomes a bad design at the end. Also, then you lost the control at some point, and it will be really tough to verify and qualify and integrate to system as well. So if you don't write some precise, compact processes, then it becomes really ugly in many senses. So we will try to do some review classes for VHDL, Verilog, and SystemVerilog. So we will try to explain more in detail during our Q&A sessions, and also I plan to do some extra streamings either in Turkish or in English for HDL code review. Okay, this was the third one. So let's continue with the fourth. A little bit resize my video. Okay, so this one, detect signals. The fourth one is detect signals and variables that are never written or read and then delete them. Yeah, this is also really misleading. Sometimes, yeah, a huge design, a huge algorithm is implemented in an ugly way, as I mentioned in the previous linting rule. And some signals are added, some signals are removed. Many different people edited that code, etc., or combination of one of those. Then signals and variables that are never written or read are flying around in the processes you have inside the .vhd, .v, .sv code you have. So it is really ugly. Also, yeah, like the previous ones, it damaged readability, reusability, understandability of that code. So you need to be careful about that. By the way, for these linting rules, sometimes you do this by you either do these manually or automatically. So there are some good linting tools, as I mentioned at the beginning, open source one or paid ones. So they do to some extent, they review your code, they use some rule sets and give you different warnings at different severity levels, like warnings, cautions, errors, notes, etc. Also, it is possible to do it manually by your colleagues, like design reviews, code reviews, peer reviews, etc. So manual and automatic approach are possible. Also, as the designer, you shall be careful. You shall be following some rules. You should be aware of the rule sets you are using in your team. So of course, as much as possible, you shall not do these issues. So it is like, first you are reviewing your code yourself, then either your linting tools or your colleagues doing that. The best is, of course, having all these three. Then the quality factor of the code increases dramatically. Otherwise, yeah, it becomes poor, and there is the possibility that having some functional mistakes as well. Also some optimization issues, as I mentioned, because you're adding everything to one process, two processes, and making it a little bit garbage. Also, yeah, that reusability, traceability issues. Also, yeah, the many negative effects are there. Okay, so fourth one, as I mentioned, you shall, or linting tool shall, or your colleagues shall find out such signals, variables, and delete them. Okay, fifth one, give high importance to code comments. It looks for brief design file. It looks for brief design file definition at the top of code, comma, reasonable comment sentences like for instance ASD or like ... kind of comments. You know, in VHDL those two dashes are that they mean it's a comment line. So the comments shall be reasonable, and processes shall start with comments as well. Yeah, last Sunday we also mentioned that those at the top of your code there should be some explanation, possibly the history, little bit history about that VHD component, who created that file, who edited for the last time, etc. Again, it depends on your company templates, but yeah, some good information about the general comments, explaining what is the purpose of that VHD Verilog or SystemVerilog file, HDL file, and comments shall be, yeah, sometimes those linting tools just check the number of the lines that's starting with that two short dashes. So it is all those comments shall be reasonable. They shall not be too long. They shall not be meaningless like that ASD kind of. So extreme details shall be added in the documentation, design documentation of that code, but some brief, strong, compact information shall be given such that yeah, the designer, other designers, your colleagues, reviewers, they can understand easily the purpose of the code. Also, if each process starts with a nice summary about the purpose of that process, this is also quite informative, quite helpful. Also, in case it is really complicated, in case you think it will increase the readability of the code, then you shall add some additional comment lines in anywhere in the code. So it is welcomed, as long as it is not very long. That kind of information shall be in the design documents, so related documents of your of that design, regarding design. Yes, I think this one is also clear. Let me check. Yeah, that's high importance to code comments. So the tools or good coding practices, looking for a brief design file definition at the top. I mentioned reasonable comments mentioned, and processes, procedures, functions, what you have in your code that shall be instantiations, anything you have important and that requires some explanations, such that it will speed up the review process, it will speed up the reusing process, then you shall add such comments. Okay, next one, check if case statements cover every state defined and detect that states. That is also important. So you need to check each and every state of your case statements. We mentioned before, it is not reasonable to have more than 16 states, because yeah, then it is more like instead of using parallel processing power and high throughput, low latency, usage of FPGAs, then if you are adding like more than 16 states, it is like the purpose becomes like using a simple microcontroller. So VHDL, purpose of VHDL is not writing some sequential codes. It is yeah, the power of FPGAs, field programmable gate arrays, are more like, or SoCs, system on chips. You can do transistor level. If your core clock is 1 gigahertz, you can make each decision, each data sampling on the, let's say you are using rising edge clock, each rising edge clock, your period is like 1 nanosecond, and you're giving decision really fast, and you can write as many processes as you may want. So latency is really low. Even if you add some pipeline stages, you are still much faster compared to majority of CPUs and GPUs, and also DSPs. I mean the chips that are working as digital signal processing units. So yeah, you need to know the strong sides of your chip, and you need to benefit from that. So it doesn't mean to have like 64 state case statements to do some, let's say, low speed communication peripheral. So there are like $1 microcontrollers for that. So also depending on the family of your FPGA you are using, you may add some soft cores to handle such sequential low speed communication issues, or let me say problems. To solve them, it is not reasonable to use a $1,000 FPGA. So of course, depending on if there are also $10 FPGAs as well, but the major point in majority of the complicated and, let me say, good FPGA designs, it do some high FPGA are used to implement low latency, high throughput signal processing. Signal includes, of course, different kinds of sensors, like also communications, high speed communication with up to 1.6 terabit per second transceivers. So the purpose is to be as fast as possible, as parallel as possible, because you have that power on FPGAs. Each clock, if you want, you can just write as many processes as you want, depending on the number of registers on your FPGA. Let's say you have 1,000 registers in that. Of course, I know this is low number, but giving just an example, you can write 100 processes, and you can assign value to those registers in 100 processes. So of course this is an exaggeration. You won't write 100 processes into a single design file, single component, because making it too much parallel, it will also decrease the readability and reusability. But power is there. Power is make it high speed, use gigabit transceivers, fast ones, read data from some sensors as fast as possible, and process them, and use some output some signals to actuators, again to use those actuators in real life, so for some different purposes. So this is the major idea, major intention, major benefit of field programmable gate arrays and SOCs. SOCs include hard CPUs and some additional ASIC IPs. Yeah, but if it is on FPGA, also soft CPUs like RISC-V, like NIOS 5 and Microblaze 5, or the previous versions of those soft cores, they are of course possible. Okay, next one. Discover the null range problems where the vector size of one argument is strictly larger than the others. This is important, by the way. It means, like, let me give an example regarding that. Let's say you have sometimes in both design and verification codes, instead of those magical numbers, some constants, some generics are used. But let me give an example from VHDL. It is like you can use down to for multi-bit vectors. You can either use down to or to keywords to define those vectors. Let's say signal my data colon std logic vector 7 down to 0. Let's say those are magic numbers right now. Normally it is preferred to have the range of that vector using some package constants or generics, such that you don't edit those vector size each time the input sizes, input widths and output widths are changing. But problem here is that sometimes also in FPGA VHDL code, the down to is usually preferred, but sometimes, for instance, to define some arrays, two keywords are also used. Then for two, you need to write it like this: std logic, like my array. Let's say, yeah, array is two-dimensional, but let's give a one-dimensional example as a std logic vector signal my state std logic vector, let's say 0 to 3, for instance, 4-bit vector. And if someone, some of those design partners, some of those designers or verification engineers made some down to 2 wrong usage, then it is nice to detect that mistake. Like, let's say if it is 0 down to 7, then the return will be null. And if you assign those vectors to some others, there will be some problems. And in some cases, you may not get an error during synthesis or simulation. By the way, newer EDA tools, newer versions of Vivado, Quartus, and Libero, they are getting more and more clever, let me say. So they are becoming much smarter. So they are detecting, compared to like Quartus 15.0, for instance, or Vivado older versions, some other old versions like 2018, let's say 2018.1. Yeah, the new ones are much active. Sometimes finding they are finding these issues, but it is much better not to trust those new versions, because you are using some of these designs in the legacy old project as well. So it is good to check those range of the vectors you have. So yeah, by default, try to use down to and check that the first value before down to is greater than the one on the right of the down to keywords. Then the result will not be null, but that the real range if it is 7 down to 0, then the range will be 8 bits, for instance. Okay, we have like 1, 2, 3, 4, 5 more and 2 nodes. Okay, let's have a 5 minute break here. And yeah, we will be back at 9 p.m. in the Central European summer time. And yeah, in Turkey time, Turkish current time, it will be 10 p.m. So see you in 5 minutes. All right, we are back. So we continue with the remaining ones. This one is about reporting duplicate file names. Yeah, this is important because it is you will have some problems sometimes in some EDA tools, some error or some random selection if you have duplicate file names. So the entity name and the file name shall match, and there shall be only one in each project. Also, it is uh, highly recommended to have only one and only one with the same name in the repository, in in a repository. So yeah, otherwise you cannot know which one of those same name entities, same name designs are the best one. So that experienced engineers shall evaluate them, shall check them, and they shall delete. Uh, they shall keep only one and delete the others from the repository. Otherwise, it will be always a myth uh, to meet uh, which one is the best one, which one is the bug-free one, or comparatively better one. So yeah, that duplicate names uh, of the files for design or verification files shall be detected, and yeah, they shall be refined. So this is the regarding that. Yeah, this analyzing cross-domain crossing. Yeah, we will have, by the way, like 2-week lecture about all those clock domain crossing, how to diagnose clock domain crossing issues, and how to apply proper solutions to those. Uh, but some linting tools, they are already doing some uh, giving some information about uh, clock domains, some clues in case there are some problems. So and the reviewer and designer and reviewer, it is not that complicated to check uh, those issues uh, fast. Of course, it becomes really tricky if design is huge and there are many hierarchies, many different components. But for each and every design, if there are multiple clocks, if multiple clocks are used in regarding HDL file, it is easy to check some basic uh, rules regarding those clock domain crossing. For instance, you cannot sample and use, you cannot read. Sampling means reading, uh, or you cannot. Yeah, let me don't give many uh, examples because it may be also a little bit tricky. But let me say you cannot read a signal from a different clock domain in the other clock domain. Let's say you have a process and your process clock is clock underscore 400 megahertz, 400 MHz. So if the signal you will be reading in that process is from another clock domain which is asynchronous to that 400 megahertz clock, then you need to apply correct clock domain crossing solution. If it is 1 bit, yeah, depending on the family and speed grade you are using, you may use dual flip-flop, triple flip-flop, or quad triple flip-flops to cross the clock domain, change the clock domain of that signal. If it is vector, there are like handshake solutions in case it is not changing each and every clock cycle, or it is relatively slow, like roughly 16 times slower from the either sometimes, yeah, it depends on the slow to fast or fast to slow clock. Uh, Slow to fast or fast to clock destination and source clocks. So yeah, it is, as I mentioned, it is a like advanced level of issue topic in FPGA design, SoC design, and ASIC design. Yeah, there are nice solutions uh, depending on the problem. But yeah, this as I mentioned, the simple level of checking in case your HDL file, HDL component using multiple clocks, then you shall do some simple checks such that, yeah, if they are not reviewed, they are not checked by the designer, then they become really problematic in the future parts of the design, because as designs become bigger and bigger, it becomes tough to find out such clock domain crossing or reset domain crossing issues. So next one, analyze reset assertions, assertions if asynchronous reset is used, if sync reset is used, and it checks its proper usage. Yeah, this one is also quite important. Actually, this is also this reset assertion, yes, asynchronous assertion, synchronous deassertion of reset, and if it is synchronous reset, the checking the proper usage of the reset, yeah, where you define the reset statement, etc. These are also kind of clock domain crossing. Yeah, as I mentioned, also reset domain crossing. So yeah, but if you don't do properly these, you are also getting many failures, many tough to solve setup and hold problems, or recovery removal problems, negative slacks. So yeah, that's why I wanted to mention that if your clock is asynchronous, meaning that if you're starting your process with if reset equal to, let's say it is active low. Okay, let's say if it is active high, because active high is preferred. We will discuss about this more in future classes. We have good design, good coding practices and design recommendation classes. Actually, we will have either 2 or 3 of them during the next weeks. But in general, if your clock is asynchronous, meaning that if you're starting with if reset equal to 1, then the reset statements, reset commands for your imported control signals and output signals, and then else if rising edge clock, then your code, what you're supposed to do, what you would like to do in that process. So this is asynchronous clock example, and in this one you shall add clock and reset to sensitivity list. And to be able to use this reset, you need a reset synchronizer in that clock you are using in the process I mentioned. So if you are using that asynchronous reset in, let's say, 5 clock domains, you need 5 reset synchronizers. So assuming that they are those 5 clock domains are asynchronous, of course. And if it is a synchronous reset, let's give the example like if then your code, your process starts like process, and in sensitivity list there is only clock, and then your code starts, then begin, then if rising edge clock, because yeah, now you don't have a asynchronous reset here, and then you add a if reset equal to one statement and else part. Again, after that if reset, because it's synchronous reset, you are adding important control signals again, like the asynchronous one. Not all the signals, because it is waste of resources if you're resetting all the signals, some internal signals inside your component, etc. So instead you're resetting critical output signals and important actually control signals, all control signals. Sometimes they are like clock enable, or like data valid, data enable, or finite state machine signals. And then in this one, you're after that if reset equal to 1, then reset signal else. Now the else part, after the else part, you are writing the code according to your design requirements. So that part is after the if reset statements else now, because you started with if rising edge clock. This is the difference. By the way, this approach in Verilog, it is easier. You don't change anything, but you just don't add if it is synchronous reset, you just don't add synchronous reset signal to the sensitivity list in Verilog. Then it becomes with the same template of the code, if becomes either synchronous reset or asynchronous reset. It is like the posage clock and negage clock, let's say. Posage clock and negage reset, let's say. And if you add that one to sensitivity list, then it becomes if it is in the reset is in the sensitivity list, then it becomes asynchronous reset. Otherwise it becomes synchronous. We shall see some examples during our Q&A session, if you ask, of course, Verilog one. But it is trivial, so you will know that, yeah, it is, as I explained, that code sequence is different. If it is synchronous reset, you start with if rising edge clock in VHDL. But if it is asynchronous, you start with if reset, then else if rising edge clock in VHDL. But it is more trivial in Verilog. So next one, check that signals and ports of, did I skip the previous one? No, yeah, okay. Check that signals and ports of HDL entity are initialized. Ideally, only control signals and output ports are to be initialized with reset. Yes, this is exactly what I explained in the previous one. So only control signals and output ports. Sometimes, by the way, some output ports are not that critical. They are not used in the upper level of hierarchy. They are not consumed, or they are just for some debug purposes, etc. Then yeah, you may not add all output ports as well. Of course, it will be nice to add some comments regarding that, saying that these are just for debug purposes on the output port description, let's say. So other signals, so that internal ones, initializations, those signal name, signal object name, let's say signal my internal signal colon std logic vector, or signed or unsigned, because those are internal, and if you are going to do some met operations either in signed or unsigned vector, so you can define them and at the end with colon equal to, you set an initial value. Then EDA tools knows that, and after the bit stream load, they start those signals from that exact value. Let's say if it is 0, it is 0. If it is 1, it is 1. So those initialization of those vectors or 1-bit signals, it is possible, and you can easily check that using signal tab, or what was the name of the Vivado logic analyzer, that initialization works. It is easy to check. So you can see on signal tab or Vivado logic analyzer that initialized values, in case you are not resetting them because they are control signals, or neither control signals nor important output ports, then you will if you initialize, you shall see those values, unless of course they are not changed until the sampling time on your logic analyzer. Okay, I think we are good. The last one, have an online linting feature. Yeah, this is really nice, by the way. Each save of a call shall generate a pop-up in case there is a warning or more. Yeah, this is usually provided in some good tools. So by the way, some open source ones are also, yeah, good means not necessarily they are paid ones. For instance, VS Code, if you load, if you install some plugins free of charge, VS Code can also do that. So online linting feature is like, as you save the file after some edits, if there are some linting problems, if there are some syntax problems, they immediately give you the warning. So you not necessarily open Vivado, Quartus, or Libero, elaborate the design, synthesize the design, so it takes too much time for each edit cycle. So that online linting feature, which are, by the way, many companies in the world are using it for software codes, embedded software, embedded hardware, so firmware codes. So it is available for many years, but yeah, since those HDL design and verification are relatively old compared to software and embedded software solutions, still some companies, some designers, some verification engineers are not benefiting from that online linting feature. But let me say it is quite helpful, because it detects the issues, the problem, the things you have done against your linting rule set, your team rules, your company rules, or some simple syntax issues. Those tools can detect immediately. All right, so I have some notes at the end. So it is not below, by the way, I will fix it. So it was at the top at the beginning. In the previous version of this presentation, but all features that we discussed shall be enabled, disabled easily. Yeah, it is like either called exceptions or waivers. So depending on the design, sometimes it is not recommended, but in some special cases, due to some necessities, and don't think like that linting rules are just, I just give some fundamental linting rule examples. There are actually hundreds of them. Depending on the rule set you are using, maybe there are 200 of them. So it shall be, those features, those rules shall be enabled and disabled, because in some specific designs, in some specific problems, maybe you need to waive them. You need to have some exceptions. Of course, that shall be approved by your team members, your colleagues. Otherwise, yeah, then it doesn't make any sense because you can disable all of them and commit and push your change. It is not acceptable, of course. With the approval of your teammates, your colleagues, then that shall be possible, because the complexity of algorithms increases, many components, many different designs, different IPs or verification IPs are combined. So in such cases, you shall have some flexibility. As I mentioned, it should depend upon the approval of your colleagues. And second note, Linting tool is a kind of automatic review that I mentioned. LT shall be supported by manual reviews. Yes, this is a good remark at the end again. Only having manual reviews, only having automatic reviews, yeah, then there is there might be some problems in such cases. So best is the hybrid solution, manual and automatic reviews together. So that, yeah, then each and every code of each and every design or verification engineer output will have a good level of quality. Otherwise, yeah, you cannot guarantee, you cannot have the similar style and similar quality level in each file, in a team, in a department, in a group, in a company. So then problems start, and yeah, like a design started 10 years ago, today some design or verification engineers, they are trying to solve the bugs, solve the issues on those designs. So this is the way to have a good design and verification libraries, IPs. Okay, so this is the end for the end of our fifth lecture. So thanks a lot for listening. Yeah, as you may know, this is our youtube.com/@falsepaths is our web page channel on YouTube. So yeah, I will be very happy if you could like and subscribe to our, like the videos, like the streams, and subscribe to our channel. So we will try to teach more, discuss more, and benefit from this know-how that we had from other good engineers and the companies I have worked, and my colleagues, ex-colleagues, current ones. So we will try to transfer this knowledge free of charge as much as possible. Thanks a lot again. Now I will have a 10-minute break. Actually, I will stop this stream and I will open the Q&A session. Yeah, as I mentioned, normally I am doing the Q&A session on Sunday mornings, but today we will have it like 10 minutes later. So I will be streaming lecture 6 in 10 minutes. So let me stop this stream now. See you in the Q&A session in 10 minutes. Thanks again a lot, and have a great evening or night. Bye bye.